collisions. An elastic collision is defined as one in which the internal kinetic energy changes. In other words, it is not conserved. An elastic collision is one in which the internal kinetic energy is conserved. Now, we're not saying that energy is not conserved. We're simply saying that it is not conserved in terms of kinetic energy for an inelastic collision. And for an elastic collision, the kinetic energy is conserved. Okay, if you find the recoil velocity of a 70 kilogram ice hockey goalie, originally at rest, who catches a 150-gram hockey puck slapped at him at the velocity of 35 meters per second to begin with. Now, we know that momentum is conserved always. Is conserved always, regardless of whether or not kinetic energy is going to be conserved, momentum is. So the goalie, so before we have a goalie who has a mass, I'm going to say G, and a V of G, and the puck, which has a mass of P and a V of P, is going to have to equal the after, which is going to be mass of G plus P and the speed of G plus P. All right, so the mass of the goalie, it's a 70 kilogram goalie, but this goalie is at rest. The puck has a mass of 150 grams, moving at 35 meters per second. The combined mass is 70.150 kilograms, and we're looking for the combined velocity. Well, we know that this term goes to zero. So the total momentum of the system before the collision is 5.25. Now, the units for momentum we kind of danced around before and didn't really address. MV is going to obviously be kilogram meter per second. And in fact, oftentimes we will either write the momentum in terms of kilogram meters per second or in terms of Newton seconds. I'm going to write it as an NS here, or actually an NSEC. And that's going to be 70.150 V. I don't normally write the units. I'm just putting it in right here illustratively. So if we divide this out, we get a final speed, really it's a final velocity, of 7.48 times 10 to the minus 2 meters per second. So in fact, this little bitty puck doesn't really do much to change the goalie from a momentum perspective. How much kinetic energy is lost during the collision? Now, we're assuming that it's lost. All right. We're going to assume that it is negligible for friction. So before, the kinetic energy was the mass of the goalie and the speed of the goalie. Okay, 1/2 mv squared. But the goalie was at rest, so for the goalie, 1/2 mg/vg squared would be 0. 1/2 the mass of the puck, the speed of the puck squared. I'm not writing an equal because these may or may not be equal. If they are, then we know it's an elastic collision. And in fact, the only way that you know that a collision is elastic is you're either going to be specifically told or you would have to determine that kinetic energy was not lost. So, since this term went to 0, since the goalie was initially at rest, the total mass of the goalie and the puck was that 70.15. So the total energy before was about 91.9 joules. After we had a total energy of approximately 0.196 joules. Okay, so How much energy was lost? Well, what we had lost was the 91 minus the 0.16, or approximately 91.68 joules lost in the collision of kinetic energy. Now, where did it go? It went into friction, heat, and so on generated by catching the puck. So you calculate the velocities